Good evening, everyone. My name is Jeremy Cartie. I am an educator at Kopernik Observatory and Science Center. And tonight we're hosting a program called The Tour of the Universe. And it's our first virtual planetarium program, so we're really excited to give this a go. I wanted to inform you a little bit about Kopernik first. If there's any new people joining us tonight, I'm sure we have a bunch of our regulars as well, so welcome to you. And we're going to take a look at our website to begin here. There we go. So here at Kopernik.org, you can learn more about all of our upcoming programs, from Friday nights to our summer camps. We're currently, the educators at Kopernik are currently organizing this year's summer camp, so be on the lookout for those. We will post those on this site as well. The link for this website is in the video description if you would like to check that out. If you want to see more of our public programs, they're right at the top here on this tab. We have the upcoming, and you can also access the previous live streams. Of course, if you're watching us through YouTube directly, then all of our videos are already there in playlists, so you can view those on our channel. But this is another way to access them, all of our previous public program live streams, including some observing streams too, which we hope to hold another one very soon. Okay, and what else did I want to mention here? If we go back home, this is tonight's program. We also have on April 24th of this year, we're going to hold a program called Race to the Stars. It's an annual program. I believe it started in 2018. And we're keeping it going. So if you would like to join us on a Race to the Stars, please join us on April 24th, and you can click there to learn more. At the very bottom, we have our clear sky chart. And I was considering tomorrow as a potential option for observing an observing live stream, an impromptu one. These are just so hard to organize at the moment. But the seeing isn't great, but it's not like it won't be good enough that we can get some deep sky. So this tealish blue here is the main problem. Everything else looks good. Cloud cover is okay. The seeing is the only one that would worry me a little bit as far as getting good clarity, but that shouldn't stop us. Things like the Orion Nebula or any planets would be fine. Like Mars, we could potentially do, since we didn't get it during the last stream. Okay. Hello, everyone. I see you in the chat here. Again, I would like to emphasize, if you have any questions during the show, please feel free to put those in the chat. I welcome it. I won't be able to get right on it as the show goes on, but we will certainly hold a question and answer session towards the end of the show, and I will go back through and look at those chats you put in. And I also like to announce your name too, for those who responded there. Okay, and if you have not seen Kopernik before, or you do not know of us, we're an observatory and science center located in Vestal, New York. This is our building, and we have 3 domed telescopes here. The 20-inch reflector is our flagship. We also have a 6-inch f12 refractor telescope. That's great for planetary viewing. And we have a 14-inch Celestron Edge HD scope as well. So those are our dome telescopes. We have a bunch of portable telescopes too. Now, in this virtual environment, we have not been able to have the public up to view through our telescopes directly, but we have been holding observing virtual streams. And you can go back and check those out if you haven't seen them before. But we're going to keep going with those. People seem to really enjoy them, and I can't wait to get back to the next one, again, possibly tomorrow. And now the other aspect, another way that you can view the night sky when you have cloudy skies is through Planetarium Software. Or at a planetarium. Now, that's another thing that's challenging to do because just like, you don't necessarily want to go to the movie theaters right now, planetariums are usually even more enclosed. So not the best place to be at the moment, but especially our planetarium, that was that's a particularly big challenge for us because ours is a portable planetarium. It's a dome, and it's a inflatable dome. You blow it up, and it blocks out all the light from whatever room you're in. You're just left with the projector on the inside that projects images of the night sky. It's a great piece of kit. We actually have two different sizes. We have one big dome that we use to bring around to libraries, schools. We're able to travel around, inflate it in a gymnasium, a place with enough ceiling clearance. And then recently, actually poorly timed, we got it just before we had to go virtual. It's a smaller dome. If you were around for Winter Star Party, you might last year in 2020, you might have gotten to try it out. It was it was a bit smaller dome that we could fit inside our classrooms at Kopernik. The other one's too big. We don't have the ceiling clearance for it. But that wasn't the intention of getting it originally anyways. But now it's cool that we can finally try it out at Kopernik. In addition to traveling around with it. And maybe what I can do, let me switch just to my camera feed for a second. I can show you this is on our channel. It's a time lapse of our planetarium inflating, just to show you what it looks like here. Oh, I wanted to go here. Just bear with me 1 second. I just thought of this. I didn't even think to show you this before, but I think it's valuable. So we will go check it out. This was from Roy Williams, another Kopernik educator, who you may know, and he recorded a time lapse of himself inflating the dome. So we'll check it out here. I'll switch back to the web browser. There it is. And it looks like that's showing. I just want to make sure it's going to play the audio. Yeah. Now it should play the audio. There it goes. It's just little music. So this is the inflation of our planetarium in the setup. It has a fan. Let me get rid of that media bar for you. The fan, it's just a box fan, a powerful box fan, but it inflates this navy blue dome here. See, it slowly inflates, even in time lapse. Can't remember what school this was. It looks familiar though. And the only piece of real structure beyond the dome itself is just a little bit of tent pole that goes in front of the door to make sure that's nice and rigid. So the door is just a zipper door. It's facing us right here. You can see Mr. Williams just went through it. And that's that. So let me go back here and I'll show you. So I don't know where'd the box go? Yeah, this box right here is our projector system, so that we just slide underneath and set it up on the inside. And you just pull power from the wall, get a nice long extension cord, and you're good to go. So let's get out of here. That's our portable planetarium, and again, we hope to give the public access to that again sometime soon. Because again, we really haven't had the chance to try out our smaller dome that we can use at Kopernik itself. So here's hoping that'll happen in the near future. Another way that you can explore the night sky at home is using your own planetarium software. And again, sorry if this is just repeated for those who tune in all the time, but I really like to stress for any newcomers that Stellarium is a great resource for you if you want to explore the night sky at home. And this is your own Windows, Mac OS, or Linux-based planetarium software. And you can even run it on a Chromebook through the Stellarium web program. So that's a web-based version. In case you don't want to download anything, that'll also work on any web browser. And I think they even have a smartphone app, although I think it's one of the more expensive ones, if I recall. They might have like a light version, but there are some cheaper versions like Star Walk or Sky Guide. Those are like $1 or $2. I think Stellarium's a little bit more. But this one is a great resource for that. And if you will, we can just pop into the web version quick. Get rid of the sidebar there. Stellarium Web should run on smartphone devices too. I think it is scalable, so you should be able to run it there as well. But the idea is you can just pan around the sky, look around, and see what's out on a given night. You can turn on the constellations. There's Ursa Major, the Big Bear. And if you want to see the artwork, see what they're supposed to sort of look like, there's the Big Bear, Ursa Major. And here's the Little Bear, Ursa Minor. And of course, at the tail end of Ursa Minor, there's Polaris, the North Star. And it does come up with some information about the objects you click on as well. So that's the web-based version. I'm going to skip on over to the downloadable version, which is a little bit more fully featured. You can do quite a bit more with it. And let's go over there. So here we're switching over to my downloaded version of Stellarium that's running on Windows. But again, you can download it for Mac OS or Linux as well. And excuse me. And same idea, but you just have more options here. So you can turn on the lines, the labels of the constellations. So here we see almost due south is the constellation of Orion. And I believe this is current time. Yes, we are at 7:14 right now, or 19:14 in 24-hour time. And you can even just keep on zooming with the scroll wheel here. Zoom, 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 and you can get to the Orion Nebula. And they basically just stick a photo from a telescope and a long exposure image of the object in question. So this is not what you'd see in the sky with your eye, but you would see that with a camera system that can take a long exposure. We did that with our relatively recent Orion Nebula stream, where we took long exposures of that object. If you want to center on things, you just click on them. If I can click on, I guess I'll click on one of the central stars of Orion Nebula. You can press the space bar, and that will allow you to use the scroll wheel to zoom right in on it rather than play with the sky there, because the sky will move on you if you're not centered. Let's see if we can show that effect. Yeah, you can see it slowly moving these stars as you zoom in more and more, and that's because it's live updating with the Earth's rotation. Now, it's all simulated. It's not from a camera system necessarily, so when you're looking out here, this is all just happening in the computer. This is just a simulation there. But some of the pictures, like the one I showed you of Orion, were real. They were taken from a scope at one point. So you can also look at the planets, and one nice way to find the planets is if we go to Sky and Viewing Options and Markings, we can turn on, if I can see it here. See, I want to turn on the ecliptic. Yeah, that'll work. And the ecliptic represents the plane of our solar system. It's where the sun will appear to move across, the planets, the moon. So this is a great indicator. It's only visible in Stellarium, right? You can sort of piece it together if you have enough objects in the sky at night, but otherwise it's just like the equator. It's an imaginary line. And we can see Mars falls along it. So we can press the space bar on Mars and zoom on in. Zoom, zoom, zoom. And there we go. There's Mars up close. And you can see Mars is sort of a gibbous phase there. And you can also see the two moons of Mars. Let's see how... This is a good comparison, because this is not the main planetarium show. That's going to come. I just wanted to show you what you can do at home for free. So Phobos and Damos, let's zoom in on those. We'll remember this. We'll see what they look like in the next program. You can see they just look like points of light there, which is about accurate unless you're right on top of them, because they are just small asteroids, captured asteroids. We also saw the Pleiades, the Seven Sisters. And here's a little satellite. I wonder what satellite that is. It's an Orbcom satellite. So there's Pleiades as well, a Seven Sisters open star cluster. So you really have everything you need for understanding how the sky looks on a given night or on a future or past evening, or even during the day. Because this is a time machine too. No good planetarium comes without a time machine. You need a time machine in a planetarium. So you can travel through time. This is just traveling through the night. And if we skip one more time, you can see it moves really fast, and then we get the sunrise. And then before you know it, because we're not in the summer yet, there's the sunset happening pretty quick. So let's see, there we go. And you can also adjust more granularly here the time, the date and time. So you can skip through the months if you want, the days, the years. The students, when we have the students up at Kopernik, they always like to try and maximize the time, and I think they figured it goes to, whoops, hang on. I think they figured it goes to like 999. Yeah, that's about as far as it goes. 99, almost 100,000 years in the future. But that's how predictable the night sky is. You really can project it out quite a bit. But notice when you go that far in the future, look how discombobulated the constellations are. Because the stars do move, they just move very slowly over time compared to the other objects in the sky, like the planets. So you can see how crazy the constellations look now. It's kind of funny. All right, let's go back to current time. And I'm going to take a brief pause here because, again, we have not gotten to the main show yet with a program called Space Engine, which I will introduce. But let me take a pause here because I see some questions coming through the chat. And I also want to say hello to everyone again as well. Oh, we have someone viewing from Boston. Welcome from Boston. Wyalusing. Very cool. I'm seeing... I missed something. Let's see. I'm seeing happy birthday, Philip. Oh, Philip is, say yes. So happy birthday to you, Philip. 12th birthday, hey, how about that? Welcome to the stream. And make sure I'm still on camera here. Sorry, I'm kind of bending over. Nicholas is asking, what is the better camera for astrophotography, a Canon T7i or a Sony a6000? I would probably say the T7i, just because I know usually the lower end Canons, not that the T7i is exactly classified as lower end, but I don't think it's a full frame if I remember correctly, just like the a6000 isn't a full frame. The T7, the Canons usually handle astrophotography better than the base Sony cameras. When you go up, they start to level out, and that's why I have the Sony A7 III, because it was ultimately cheaper with roughly the same or similar performance to a similar rated Canon, which is one of the R level Canons. It's a full frame camera, so you can capture a lot of light there. But I would say in between those, the T7i is probably the better. I haven't been super impressed with what I've seen from the A6000s. Western New York, just south of Buffalo. I have a lot of family in Buffalo there. Welcome, Brenda. We'd love to have you visit as well. Yeah, we did. Lynn is asking, did you guys bring that planetarium to Binghamton University a while ago? And we did. In fact, that was the last time I used it personally. I brought it. I can't remember the program now. It was February 29th. I looked it up the other day because I knew I was trying to figure out when the last big program we had with it, and I'm pretty sure that was the one. So February 29th was the last show, and that was at BU. So yeah, and we brought it there before too. We brought it to BU a number of times for their events. Oh, thank you, Dr. Gayash. Dr. Gayash says Stellarium is $10 on iPhone. So yeah, it's a little bit of a pricier one. So if you're going for the phone versions, there's some free software, or you can get like a couple dollars for Sky Guide or Star Walk. So Brenda's asking, how do I get Stellarium in Windows 10? I can go back to that web page quick here and show you. Again, if you go to stellarium.org, it's probably not quite legible, but let me put it in the chat here. Again, my username is going to show up as Jeremy DC tonight. So if you go to that website, I just put in the chat stellarium.org, that will take you to this page where you can download it at the top here for Linux, Mac OS, or Windows. Probably you'd want the 64-bit. Or you can just run it through the web. Okay. All right, and I think that about covers the initial questions here. I don't mind doing 2 phases of questions like that, but for now, I'll probably just stick in Space Engine for a bit, and then I will get to your questions at the end of the show. So we'll just like a traditional planetarium show, right? If you've been to Roberson or any of the great planetariums across the country, then or if you've been to the Kopernik Planetarium, then I'm sure you're familiar that they usually handle a Q&A session at the end. So we'll treat it similarly here, and we saw Stellarium. That's something you can run at home, and that's focused looking up from the Earth. So at a given location on Earth, you're looking up at the sky. Space Engine is more about looking at the universe as a whole and the solar system as a whole and traveling around. So almost like you're on a spaceship, a super fast spaceship, because the rate at which we're going to move through the solar system and the universe is not possible, at least with our current technology, for sure. But even like when you factor in the speed of light, you'd have to be talking about like warp speed and stuff at the rate we're going to be moving here and traveling. So worth keeping in mind there. This is not realistic in the traveling sense, but what's really neat is that we can do this from our computers at home and explore space in that sense. It's powerful, even if it's virtual. And the other neat thing about this software is it is also virtual reality compatible. So if you have a VR headset and a decent computer, that's the one trick with this software. It's not like Stellarium that you can basically run it on everything. It's pretty intense graphically. So you do need either a really modern CPU or a combination of a fairly modern CPU and a dedicated graphics card. That's probably the good way to run it. So effectively, if you have something like a gaming PC, or just any computer with a graphics card, you can run Space Engine without too much trouble, but it's not something you can run on a Chromebook or an Ultrabook. It's a bit too intense in that regard. So we're gonna give this a try again. If you want to download Space Engine, I think you do have to pay some money for it. This is not a sponsorship, by the way, in any way. This is just we're using it for educational purposes. But I just want to inform you, if it's something you want to explore, you can get it through Steam. And I think we posted in our email today that went out their website and a video about it. But you can, of course, learn more just doing a quick search of Space Engine. Okay, and without further ado, why don't we get right into the program here? into our exploration of the solar system and beyond. Okay, skipping over to Space Engine, and there it is. There's the start of it here. So we're going to start with our home planet, the Earth. And you can already tell, very different from Stellarium. Stellarium doesn't really allow you to travel to objects or look down on the Earth. It's designed looking up from the Earth or looking up from another planet. You can change locations in that way. Like, what does the sky look like on Mars, for instance? You can do that through Stellarium. But you can't fly away from Mars or fly away from the Earth and look at the solar system and the universe as a whole. So, but that's what we're going to do here. And we're starting with our Earth. And the neat thing here is we can really just do a nice pan around, sort of orbit around our planet. See if I can get to those. I don't want to expand it though. There's some bottom controls that I would like to get to, but I cannot see them because I'm in windowed mode, so I might have to fix that in a bit. They don't want to show up at all. Okay, well, we'll work without them. I missed that by accident. Anyways, so we're orbiting around the Earth. And you can see the night side. Of course, we've moved into the night. So this is roughly live. It's a little bit ahead, I think. But you can see we're over here, right, in New York. At least that's where we're located, in the Vestal, New York area. Perhaps you're located elsewhere in the United States or in the world. And a good portion of the world is in darkness right now. You can see from South America, North America, Europe, and Africa are all in darkness. And then if we swing around here, the Pacific Ocean makes up a significant portion of our planet. So it's in the daytime still. So if you're in Hawaii, or if you're in Australia, or if you're in Asia, then you are still in the daytime. And you're panning around back to the other side. You can also go down to the Antarctica, to the South Pole, and go up to the North Pole. And the resolution of these worlds are very impressive. So if I go over to this nice piece of Australia here, you can really zoom in, and you can just keep zooming in. It's not quite Google Earth level of clarity, but you get quite a nice texture there of the surface detail. And considering this has more than just the Earth, that's pretty impressive. That you can see some really nice satellite imagery of land masses on the planets as well. Some nice cloud layers too. All right, so we'll zoom out a bit here. Now, we want to maybe go explore our nearest terrestrial neighbor, or extraterrestrial, I guess you'd want to call it, right? Because Terra means Earth. And we're going to go on the hunt for the moon. Where could the moon be? We're seeing some planets. You're seeing the plane of our solar system here. So these are definitely planets. These bright objects. Now, I think we're approaching new moons. Could be why I'm having trouble right now. Nope, that's Venus. So let's go and grab the moon. Ah, there it is. Yep. Yeah, you can still see it. It's a bit of a crescent there. You can just about make it out. Now, I'm going to fly. We're going to slowly fly to the moon. Again, a lot faster than you would if you were in a rocket ship. If you're in a rocket ship, it takes about 3 days. This is going to take, seconds. 20 seconds to be exact. So we'll take a nice gradual trip to the moon. Seeing a nice view of the Milky Way as we travel. Right over here. There's the moon. And we've approached it in a way that it's showing the current phase of the moon there. So this is a nice, relatively fine crescent that we're seeing. Could be a little bit finer. Like you could definitely, in the next day or two, it's going to be nice thin line, then it'll eventually be a complete new moon. Full new moon is a little bit confusing. So you get some nice crater shadows there along the terminator. Just like you would if you were taking an astrophoto of the moon. So it's simulating natural light from the sun. So the sun is actually a light source in this program, which is important if you want to get these nice crisp details on the craters. So our newest planetarium software works very similar to this, where you're able to simulate the actual light from the sun and get some great shadows on the different worlds in the solar system and even in other solar systems. So it's very similar. This just happens to work really well on a flat screen rather than projecting it out onto a dome like we can in our planetarium. Okay, and you get some nice views of the mare. It's not much different from when we viewed through our telescopes. The trick here, though, is that we are able to view the other side of the moon, and this is actually what the other side of the moon looks like. The moon is tidally locked, so we cannot see the opposite side of the moon. That side is always facing away from us, but that should not be confused with it being a dark side of the moon. It's not a dark side. It can be in darkness. It's about, a good portion of it is in darkness half a month, but it's not always. It's in darkness the same amount of time as our side is. So there's no dark side of the moon. It's just a side that's always pointed away from us. And there's evidence for that here, because one half of the moon always has to be exposed by the sun, like you're seeing there, right? This is the side with the sunlight. This is the side without. We're seeing something like this in our current, from our perspective here on Earth. So right now, especially as we approach new moon will look like that, and it'll be very, not right in front of the sun, because that would mean it's an eclipse, but around the sun, and it would be in full shadow like that. So that means we'd be seeing the dark side of the moon, but it's not one side. It's just depends on the time of the month there. That will depend on what part of the moon is glowing and what's not. And we can even zoom a little bit further in, just like the Earth, and get some really nice crater features. And this is all based on satellite imagery. So again, this side that we never get to see, look how heavily cratered it is. Our side's heavily cratered too, the one that we always get to see, but we have a good portion of the seas, the mare, these dark spots. So the opposite side doesn't have any of those. It's mostly just a cratered surface. Looks very much like Mercury. Okay, so orbiting around our moon. We only have one moon. We have a bunch of satellites now, though, and those are man-made satellites. The moon is a classical satellite, though. We distinguish them from natural satellites. So the moon is a natural satellite. Our satellites are artificial. But we have a bunch of them around our planet. Okay, zooming a little bit out from the moon. Why don't we now take a tour of the planets? We've checked out the Earth, so we'll skip that one. But we're going to go right in a row. But we're going to begin with the star of our solar system, the sun. So let's take a gradual excursion to the sun. There we go. Okay, I was finally able to get rid of my Windows taskbar, so now I can actually see the controls I want to. So now we've taken a trip to the sun, and here it is. I want to center in on it a little bit better. There we go. So it's speckled with sunspots. Sunspots are cooler regions across the surface of the sun. We can see them through a appropriately equipped telescope. Now, if you have a telescope at home, never look at the sun. unless you're an adult and you know exactly what you're doing with filters and the like, or projection. Otherwise, if you don't know how to safely view the sun, don't even attempt it. It's too dangerous, and you can potentially go blind in one or both of your eyes. But at Kopernik, we have filters, and we're able to see these sunspots through our telescopes. And we can see them here. Now, the exposure level has been toned down a lot in this view of the sun. If we were right next to the sun like this, like there's a satellite that travels around the sun called the Parker Solar Probe, and it's getting really up close and personal with the sun, and only able to last, within millions of miles of the sun for a short time before it has to jet back out and cool down, because otherwise it would get way too hot. So the exposure levels tone down quite a bit here. If we want to get a sense of what the sun would be like, if you're right up close, you bump up this exposure level down here and look at that. Oh dear. Oh, it's blinding. So we're going to bring it back down to a auto adjust exposure level. Actually, I think a better example is to turn off the HDR. No, I guess HDR is the best one to be on, because there's also automatic, and that adjusts to the exposure of the object even better. So now we're really toned down the light. Or we can adjust it to manual, and we can just control some manual focal and exposure options. So there's some nice, there it is. Yeah, that's what it would look like. But the HDR mode sort of exposes for multiple levels and multiple brightnesses. So these specks are sunspots. They are features on the surface of the sun. Sometimes you can confuse, some dust particles and spots for sunspots. So you want to make sure your lenses are clean when you're viewing the sun. So we can orbit around the sun here. And of course, because the sun is the light source of our solar system, it radiates in all directions. There's not going to be any dark or light side. This is the reason there are dark and light sides, or where there's a terminator of planets, because the sun is putting out the light, just like a light bulb. You can, hold your hand up to a light source, and one side of it will be shadowed, the other side won't. It will be lit. So that is our parent star in our solar system. And this one can zoom in a bit too. Although the sun, as far as detail goes, it has a lot of these wavy patterns across it. And this does not show you any solar flares, at least at its current settings. It's only showing you the sunspots at the surface level. But around the edges and across the surface, you'd also get some solar flares, these big solar eruptions. And sometimes they are so powerful that the flare breaks apart and you get a huge solar storm projected out into the solar system. And that's what can wreak havoc on our electrical grid and our satellites. So we're always watching the sun so we can be as prepared as possible for those events. Okay, zooming out here. There's our sun. As you zoom away, it does expose to a level that's more appropriate for the sun. It's really bright there. But when you zoom in, it lets you see some detail. Okay, so now we're going to move on to our first planet. The first planet from the sun is, maybe you know, it's Mercury. So let's go. Oh, I have a friend joining me. Sorry if you. I'll show you quick here. This is Kylo. Kylo is our new cat, and he joined the stream now. I'm not sure you can see him when he's just on my lap here, but you might hear him. He's a very audible fellow. He might be knocking the microphone. Apologies for that. He just came to greet us for a short period. Okay, moving on to Mercury here, our first planet in the solar system. And it's targeted. This arrow is showing it targeted. So we're going to go take a nice trip, a 20-second trip to Mercury now. Again, way faster than you can actually get there through traditional means. And 5 seconds to go. All right, and here's Mercury. And as I said, we might even want to bring the exposure down on this one just a bit to get more detail out of it. This one is very much like the moon. It's a cratered surface. And you can see the temperature here is 126 degrees Celsius. Whew, that's quite hot. Again, like if boiling temperature of water is 100 degrees Celsius. So it's even more than that at its surface. Now you might think, first planet from the sun, why only 126 degrees Celsius at the surface? We'll find more about that, because it doesn't seem too different from the Earth, for example. A nice temperate day, or like room temperature, so comfortable temperature for humans, is like 25, 26 degrees Celsius, something like that. So this is, it's 100 degrees Celsius more, so it's certainly hotter, but it's not, it's not like it's the same temperature as the sun, even though it's relatively close. So that's Mercury here, and we can even travel through time a little bit. Mercury, I believe, has an orbit of 66 days. Oh no, sorry, 88 days. I always get that confused. I always say 66, and it's really 88. Orbital period of 88 days here, and a rotational period of 58 days. So similar to the moon, where you have the rotation period of the moon matching up with its orbital period. So the moon will rotate once every time it orbits the Earth. Mercury is very similar to that. It will rotate once every time it orbits the sun, or very close to that. It's still like a 30-day difference, or they say 2 to 3 ratio there. But it's very close, very similar. It's in nothing like the Earth. The Earth rotates every 24 hours once. We have 365 days to get around the sun. That's a big difference compared to something like Mercury or the moon. Okay. So it's also worth noting, since a significant portion of of Mercury will be in darkness for a significant portion of its orbit, the darker side will be cooler compared to the more temperate side. And Kitty says, is it that it's an average of both day and night? That might be the case, that this temperature is an average between the two. I can't tell you for sure where they get this specific number, but because as I said, it does seem a little bit low at first glance. But that might be the case, because the dark side of the moon will be colder compared to not the moon, of Mercury, will be colder compared to the bright side. And that's like similar to, how you expect the desert to behave on Earth. When there's no light and it's nice clear skies in the desert, all of that heat is just going to escape and radiate back into space. Now we have an atmosphere to sort of seal that in. Mercury doesn't have that at all. So there's no way for it to retain heat if it's in darkness from the sun. So very cratered surface, very much like our moon, but much hotter. So we can think of it as a hot moon. But of course it's not a moon, it's an individual planet. All right, let's go to the next one. Second planet from the sun. Ooh, what is it? Does anyone know what the second planet from the sun is? Yes, it is Venus. We're going to go to Venus now. Take a nice trip to Venus. Each of these trips is 20 seconds. So we'll take a nice gradual approach to the hottest planet in the solar system. That is, might strike you as odd at first. You have Mercury, which is the closest to the sun, but then you have Venus, which is the hottest planet. Now, how does that work? Well, we've added a new term here to our list, and that is atmospheric composition. So the atmospheric composition of Venus is carbon dioxide, heavily carbon dioxide, and nitrogen. It also has a bunch of sulfur oxides in there as well, sulfur dioxide. But those are the two principal components of the atmosphere. And it is an extremely thick atmosphere. Here on Earth, we have an atmospheric pressure of 1 atm. That should make sense because that's what the unit is based off of. So we have 1 atmospheric pressure. Venus has 92 for its atmospheric pressure. 92 atm. That's incredible. 92 times as thick as our atmosphere here on Earth. That's the reason why it's able to retain as much heat as it does. Venus has a runaway greenhouse effect. And, that's one of the things, we're trying to escape here on Earth, right? Now this was naturally a natural greenhouse effect. Venus is a very active world, lots of volcanoes, lots of gases just spewing into the atmosphere, lots of carbon, no oxygen, and carbon dioxide is a greenhouse gas. And that greenhouse gas is able to trap in all of that heat, especially at this atmospheric thickness. Now that's the one difference there. We're not going to end up like Venus anytime soon because we would have to pump a ton of gases into our atmosphere, and it would need to thicken up much more than it is, and a significant component would have to become carbon dioxide. However, that does not mean that it's not a problem. In fact, it is an extremely big problem. As adaptable as humans are, if we let the carbon dioxide makeup in our atmosphere get too high, it simply will drastically and dramatically change our planet. Not again to these temperatures here. It's not going to be 514 or almost 515 degrees Celsius at the surface of the Earth. Because one, if you had the same atmospheric pressure, it's basic science. There's more energy hitting Venus than there is hitting the Earth. Venus is closer, more intense energy. So even at the same atmospheric pressure levels, Earth would still be cooler, even at the same atmospheric composition. But as far as life is concerned, small increases in temperature, average increases in temperature, will dramatically change our planet and our biology, our biosphere. So that's the issue there. It's not going to end up quite like Venus, but Venus is a testament to where you don't want to be. And it should be taken as such. Now, you may wonder, why am I talking this way about Venus? Well, part of the problem with Venus is we don't get to see much. Venus's atmosphere is so thick, there's so many clouds that we cannot pierce through its layers with visible light. You need infrared light or some other wavelength to look through the atmosphere. And I believe there is a way to peer through those clouds here. I think we can even land on the surface. Why don't we try that? We're going to go here, land on an object. We're going to land on the surface of Venus. And we can enter aircraft mode. Yep. And we can fly around a little bit. Bump our speed up here. There we go. And we can see almost like these dune-like structures on Venus. Now, this is mostly simulated. As you get higher and higher, there will be some surface features that we've been able to map out through infrared data. But it gives you a sense of the land structure. We can go a little bit higher, but as we go higher and higher, we're entering into the thicker atmosphere, and there you go. See, we're peering back amongst the clouds and heading back out into space. So there's also a flight simulator mode to this, which is pretty neat. Oh no, we're flying. Let's get back here. There we go. Zoom out. Zoom out. So there's Venus, the hottest planet in our solar system. Where shall we go next? Well, we already traveled to the Earth, so what comes after the Earth? Our homeworld. Well, it's a planet that has been in the news recently quite a bit. That is Mars. So let's take a trip to Mars. Again, skipping over the Earth because that's where we started. Ah, there we are. So here's Mars, the red planet. The fourth planet from the sun. And, you know, the red is a little bit deceiving, right? It's not because it's hot. It's quite a bit cooler than our planet, average temperatures being negative 63 degrees Celsius. And lost my train of thought. So, yeah, the average temperature is quite a bit lower, right? I guess if we quickly bounce to the Earth, let's get a look at the average temperatures of the Earth. Whoops. So we're bouncing to the Earth here. We did a little bit faster that time. There is a way to go faster. So average temperatures being 14 degrees Celsius. For Mars, we're looking at negative 63 degrees Celsius. Now, that's not to say it can't be somewhat warm on certain areas of Mars. If you're near the equator, you know, at shallower latitudes, even around our latitude, like comparative latitude of like 42 degrees, that will still, during the summertime, won't be too bad. You know, you might be in the low, like you might be in the 30s, or near the equator, you might get up to 70 degrees Fahrenheit. Pretty comfortable temperatures. But the atmosphere is much thinner. As you can see here, the atmospheric pressure is 0.012 atm, so much lower than our planet Earth. And the atmospheric composition is carbon dioxide, argon, and nitrogen. So similar to Venus, where a significant component of the atmosphere is carbon dioxide, and again, carbon dioxide is that greenhouse gas. However, it's just not thick enough to be a contributing factor to warming the planet. Now, that is a potential way. You know, it's as thought experiments, scientists have thought about, could you terraform Mars? There's so much potential trapped carbon dioxide, for instance, in the ice caps. Could you use that carbon dioxide and burn more of it into the atmosphere, make it thicker, and produce a greenhouse effect? You know, it's sort of what we don't want to be doing here on Earth. If we could somehow, transport all our carbon dioxide to Mars and put it in its atmosphere, thicken it up, and warm up the planet, that's if you could do that, in principle, you could warm up Mars. But of course, that's not a feasible thing to do. So there is CO2 in the atmosphere, not enough to really contribute to a significant warming effect because the atmosphere is too thin. That's why the blades of the Ingenuity helicopter are so large. They need larger blades to create the necessary lift to pick up the spacecraft, the little helicopter box off the ground on Mars. So they need to have bigger blades for that lower atmospheric pressure. Now here we have the caps of Mars. It's hard. Let's see, where are we here? I think that's the southern cap, and up here would be the northern cap. I might be disoriented though, because just at this point we've traveled around enough and we've rotated our view enough that could be upside down. I think this is Syrtis Major though, so that looks about right. And I think if we travel through time, we should be able to see Olympus Mons. So let's go skip forward in time. The rotational period of Mars is about 24 hours. It's just about a half hour more than our planet's day. So 24 hours and 37 minutes, it says in here. And that's how long it takes Mars to orbit once. How long it takes to rotate once. For the orbital period is 1.9 years. So almost 2 Earth years for Mars to get around the sun in one orbit. We got to go a little bit faster here. There we go. Now we're moving along. We're moving 1,000 times faster through time. And these little bright objects around Mars are the moons, Phobos and Damos. And as I said, we can compare this to Stellarium and see just how powerful this software is. We can go visit those moons, unlike Stellarium, which we weren't able to. Because again, Stellarium's trying to simulate the experience on the ground. This is able to experience it as if you were to travel around the solar system. Here's some of the volcanoes appearing on Mars. There is Olympus Mons, the largest volcano and mountain in the solar system, bigger than our own Everest here on Earth. So this is Olympus Mons here. It's a not dormant, an extinct shield volcano. And you can zoom right in on it. I wonder if we try and land near it here. Will it let us land? Yeah, we're gonna land right on top of it. So here we are, like as if we were the rovers of Mars, right? Traveling around on the surface. And now let's take off from the surface. Boost up our speed again. And fly away. I think if we move straight forward here, we'll see Olympus Mons. As if you were flying on an airplane on Mars. Let's fly a little bit above the atmosphere and get our bearings to see if we can spot it. Oh, yeah, actually, I think we're on top of it. As I said, though, like it's a pretty gradual climb. It's a shield volcano, but it's just a massive shield volcano. So I think this is the caldera here that we're flying over right now. So you can really, there's the rim of Olympus Mons we just flew over. And you can see this nice atmosphere that we're flying amongst. Okay, so let's switch back over to navigation view. So you can see the planets. You can see Val Marineris right over here. That is the huge crack in the surface of Mars, and it's the largest canyon in the solar system, bigger than our own Grand Canyon. In fact, the width of Val Marineris is about the width of the United States. So certainly bigger than the Grand Canyon, right? It's a massive canyon in the surface of Mars. And you can also use it as a bit of evidence for the flow of water, right? There's a lot of pieces of evidence here, but just look at these streams, basically, across the edge of Val Marineris. There's evidence like this all over the surface of Mars. Like you get at the end of Val Marineris, you get almost like these deltas, right? Spreading out and moving into different potentially ancient bodies of water. And that's how the Grand Canyon formed, right? From the Colorado River. Colorado River carved and carved and carved into the surface of the Earth until you're left with this massive canyon. You can see similar features across Mars here. And that's just one example. You get these streams. Now, there's no flowing water on Mars anymore, but there's plenty of ancient evidence for it like this. You don't see this on the moon. You don't see this on Mercury. But you do see these features that are so similar to our planet on Mars. Of course, you do get moon-like features like these craters. Mars doesn't have a thick atmosphere, so there's going to be more craters across its surface. Our atmosphere protects us in that sense. But I think there's far more Earth-like detail than there is moon-like or crater detail. And that can be seen just stretching across the planet all over. Really nice high-resolution view here. All right, let's go take a look at the moons, Phobos and Damos. So this one is dwarf moon Damos. It orbits every 30 hours and has a rotation period of 30 hours. So again, sort of like a tidally locked situation with this moon. So its orbital period matches its rotation period. And there is Damos. Again, a captured asteroid. It's not big enough to be a spheral. So it's not sphere-like, a spheroid. It is more irregularly shaped, like we'd expect from an asteroid. All right, and we'll go to Phobos next. Let's see if we can find it first. There's Mars. As if you were standing on Damos, that's what you'd see of Mars right now. Isn't that neat? Where are you, Phobos? Are you in darkness? Are you getting eclipsed? Phobos. Oh, it might be getting eclipsed, yeah. Well, look at that. We found a Phobos eclipse. Never know what you're going to find in Space Engine. So this is an eclipse of Phobos, so it's actually in the shadow of Mars. Because it's such a small world, these eclipses are very different from our own like lunar eclipse, where we would get a nice red glow on the moon, partially because the moon is so big that would become pretty apparent to our eye. Phobos is small enough where that would be less likely to really make out. That glow, that red glow, of course, comes from Earth glow. So light bouncing off the Earth and through its atmosphere and hitting the moon. We're not seeing that here. Okay, let's skip ahead in time, though, and see if we can get Phobos to come out of the eclipse. There it went. It popped into view. So here's Phobos. Now, Phobos is interesting because it has it's a quicker orbital period and rotational period. They match up again. 7 hours for it to orbit around Mars. And it's actually on a decaying orbital path. So eventually Phobos will crash into the red planet. Not going to happen terribly soon, though. So if you want to be an astronaut and go explore Mars, don't let Phobos stop you. It's not something you'd have to worry about anytime soon. But we do know it's on a decaying orbital path. So someday we'll crash in. Look at that view. How about that? If you're on Phobos, you see this nice atmospheric glow of Mars. And you get a nice view of the sun there. All right. I want to go to Mars one last time because I forgot to really mention where does this red color on Mars come from? And effectively, it's iron oxides. We have, which is rust. We have rust here on Earth. When rust gets exposed to oxygen, when iron gets exposed to oxygen, you get iron oxide, and that's rust. And that's where the rusty color of Mars comes from. If you just dig a little bit under the surface of all this rusty dust, it ends up being a little bit more like this darker, these darker features here, or maybe like a grayish color. The rovers have done that. They've scooped up off the surface and they've uncovered what's just underneath these thin layers of dust on the surface of the planet. Now, in some areas it's much deeper, but on Mars, or rather, where the rovers are, usually it's thin enough that they can just scrape it off the surface and see what's underneath. So that's where the red color of Mars comes from. It's not because it's hot. It's because it's iron oxide. It's rusty. Okay. So we saw Phobos, Deimos, and Mars. Let's go on to the fifth planet from the sun, which will be Jupiter. Now here's Ceres. Ceres is an asteroid. It's commonly referred to as a dwarf planet now, much like Pluto. It's actually, let's go to it. It's right here. Ceres is found in the asteroid belt. I believe the Dawn mission flew by Ceres, so we actually do have nice detailed images of the surface of this world. Oh, I gotta go. There we go. So you can look those up, but this is effectively what it would look like in those images. This is taken from that NASA data. And you can see it's a cratered world because it's in the asteroid belt. That should make sense. There's no atmosphere, so just like the moon or Mercury, there's no atmosphere on it. It is spherical. It's like more of a spheroid. It's a little bit oblong, but it is mostly round, so it is considered a dwarf planet. But if you want to refer to it as asteroid, that works too. But it's in the same category as Pluto. Got some nice mountain ranges across it. Nice big craters. Now, of course, it's a fairly small world. Let's see, where do we have the diameter is 938 kilometers. So it's relatively small. That's not, you think of 1,000 kilometers. That's not very far here on Earth. So it's small, but what is its orbital period? 4.5 years looks like for it to travel around the sun. And there's so much interesting data to inspect here, which is why I love this program. And I really can't list it off for each one, but talking about the gravity, it's 0.03 Gs. So if we consider Earth gravity is 1 G. This is 0.03 Gs. So much lower gravity. It'd be a similar experience to, you see the astronauts bouncing around the moon, but this is even smaller than that, so you'd be even lighter on Ceres. Average temperature of negative 116 degrees Celsius, which is fascinating, isn't it? That's not too... negative 116 degrees Celsius. So it's not like incredibly different from Mars there. And this doesn't have an atmosphere. So that really goes to show how thin the Martian atmosphere is. I think Mars was like negative 60 average temperature. This is negative 116. So just getting rid of the atmosphere and even moving, this is further away than Mars. It's not that different. So make sure you have a spacesuit when you go to Mars. Or if you go to Ceres. That one's more obvious. Okay. That is the dwarf planet Ceres in the asteroid belt. Next up, the fifth planet from the sun is Jupiter. Let's take a gradual flight to Jupiter. Right into the Milky Way. Look at that. Milky Way is, of course, our galaxy. We're living within our galaxy, so we're only going to see part of it, and that's where you get this nice concentration of gas, dust, and starlight, and you get that nice band across the sky. Okay, so here's Jupiter, the largest planet in our solar system. I keep losing track of... There it is, diameter. So we are at 139,822 kilometers for its diameter, a massive planet. And we can see here it rotates every 9 hours. Yep, I recall that. Or almost every 10 hours. It is a pretty quick rotation, so it'll rotate multiple times within an Earth day. Almost 2.5 times it'll rotate. It has an orbital period of almost 12 years. 12 years to get around the sun. Whew. And it's, of course, famous for its big red spot, the big hurricane system. And, it's almost a different beast entirely because it's so massive. Like, I think at its largest size, you're able to fit like 3 Earths across the Great Red Spot. Give you a sense of the size. It's like 2 to 3 Earths. Incredible. Incredibly huge storm. And there's similar hurricane systems down here. But like I said, it's not really doing it justice just to call it a hurricane because this storm is massive. Put all the hurricanes that have ever happened on Earth, and I don't even know if you combine their size, and I don't know if you'd even reach the size of the Great Red Spot. So massive storm system. It just keeps going. We know it's been happening for hundreds of years since Galileo first observed it through his telescope. But it just keeps on going, and sometimes it starts to get smaller. It seems like it's a bit smaller right now, for example, but it might gain energy back and increase its size again. So it keeps on going. We have all these nice different gas bands across the surface. These come in really well through telescope observing, either with your eye or through a camera. You can see these bands, and if the Great Red Spot is there, you can see the Great Red Spot. So there's the great big planet of Jupiter. If you've ever seen the Space Odyssey series, that movie treats it as a failed sun, and they spoilers. It's an old movie, but I think in the second one, it's 2010. It actually completes that journey of becoming the second star of the solar system, because it's effectively made out of the same material as a star. It just doesn't have enough of it for it to start burning and go through the process of fusion. So hydrogen and hydrogen combining together to create helium. It just doesn't have the mass to do that. So that's why you think of it as a failed star. But, just give it a little bit more mass and it could, ignite. Now, Jupiter has many, many, many moons. And we're not going to even be able to see them all through Space Engine. We're going to see the big ones there, the 4 Galilean moons. They're in a really cool orientation where you're looking from above, like a Y shape. But there's also a few of the smaller moons too. There's even more than that, than what we're seeing here. There's tens of them, 60, 70, 80 moons. I can't remember exactly what the number is, because they just recently discovered more. They discover more moons around these objects all the time amongst Saturn and Jupiter, and they like to fight over who has more moons. As we discover more, science just seems to go that route and oh wait, Saturn has more moons. No, Jupiter has more moons. That's now if you really consider every satellite that's orbiting Saturn, every little pebble, in the ring system, then of course Saturn has more. But that's not really how we classify those objects. All right, let's go tour the moons of Jupiter, at least the 4 Galilean moons. If you've watched our observing streams, you've definitely seen these in the scopes. They are visible. So here's Callisto, mostly a cratered world. Some interesting features, though, like this cracked region, or looks like an ancient impact there. Some nice color gradients across the surface as well. It's an icy world. Many of these moons around Saturn and Jupiter are going to be icy worlds. That's not so much rocky. When you go into the outer solar system, there's not much rocky material to work with. A lot of it is trapped in the planets in the inner solar system or in the asteroid belt. Once you get beyond that, it's a lot of icy material or gaseous material. And that should make some sense. The heavier stuff and the formation of the solar system, the heavier stuff will be more dense on the interior, and the lighter stuff will push out towards the exterior. And that's how the solar system is organized. So there's Callisto. Let's just zoom out here, and we'll go to the next one. I'll be able to remember which is which here. So we'll go to the other end. This is Europa. Europa is thought to have a subsurface ocean with more water than our planet. So it has a huge thick layer, again, because it's a mostly icy body, it has a huge thick layer of ice. Oh, I'm just getting word that my camera died. All right, well, you can still hear me, and that's okay. You don't necessarily need to see me. Thank you for the update, though. It's one thing I need to fix with this setup is making sure I have a steadier power source. Unfortunately, it can't supply enough power while it's running to do that. So we'll work that out the next time, but I'm glad you saw me in the introduction. And thank you, Kitty, for letting me know. And also, I see the comment just above. Linda says Jupiter has rings also, and it doesn't. It does in fact have rings. It does. A very thin ring system compared to a very wispy one, low density compared to Saturn, but it does have one. It's not simulated here from what I can see. But yes, Europa has all these cracked features in the surface, and these cracks are thought to be areas where the tidal forces of Jupiter breaks apart the icy surface, and then the liquid water underneath rises up, fills in that gap, and oh, look at this nice detail down here. Some areas are more detailed than others because that's where good images from the satellites were able to take pictures. So you get these nice areas of really high clarity, either from the Voyager probe or probes or the... I don't think Juno takes many images of the moons from what I've seen so far. I think Juno, the spacecraft that's currently orbiting around Jupiter, is pretty strictly taking images of surface data of the planet itself. I think it can take images of the moon, but I haven't seen many. But yeah, these cracks, they open up from the tidal forces, they cracks into the surface, and then the ocean underneath rises up, fills in the gap, and freezes over. So the surface of Europa is constantly changing because of that. It's very dynamic. There's cracks all over. There's a nice big crater there too. So, you wonder, is life possible in the ocean of Europa? Could there be life in that subsurface ocean? We don't know, but it does. We can theorize. We can, if the ocean is too salty, for instance, more than likely life can exist there. So that's one area we can really get a good idea. If we can somehow send a spacecraft either to drill into the surface and enter that subsurface ocean, or if we can, get lucky and get into one of these cracks here, that might be where you'd want to drill to begin with, because it's a newer or weaker ice structure on the surface. Could you go and measure the salinity and the makeup of that water, of that subsurface ocean? That's a possibility and something NASA is looking into. Okay, zoom away from Europa. This one here is Io, spelled just like it sounds, I-O. And, oh, wow, look at this one. So interesting. Look at those bright spots across the surface of the planet. This is a volcanic world, very active. And you may wonder, all this activity in the outer solar system, further away from the sun, how is that possible? Well, Jupiter's tidal forces actually are a source of energy for these worlds. Just like with Europa stretching and pulling and cracking into the surface, the inside of Io can be warmed and heated because it's being stretched and pulled by Jupiter, and it's even closer than Europa. So this is a very volcanic world. It has way more volcanoes than even the Earth across its surface. Very active, and you can see its color sort of matches up with that, right? You relate volcanoes to sulfur deposits and things, and that's what its color signifies. So Io has a lot of sulfur across its surface because of these volcanoes all over the planet, or the moon, excuse me. Now, I say the planet, the funny thing about that is if these moons were not orbiting Jupiter, if they were just orbiting the sun itself, they would most certainly be planets. They are large enough for that. Like the next one we're going to view here, another icy moon, the last one, is... Oops, that's Callisto. Wrong one. Got to reorient here. Ganymede. And yep, here's Ganymede. Ganymede is very cratered. Some cracks in it. It's further out, so it's not as active as the interior ones. But Ganymede is the largest moon in the solar system. It's bigger than our own moon. In fact, our moon is like third or fourth, I think. The Titan around Saturn is another large. Checking the time here. Oh wow, okay. Is another large moon, the second largest moon, but Ganymede is the first. Another icy world. Okay, we might only get through the solar system tonight, which is okay because we can always come back to this program for future planetarium shows. If that's something you're interested, let me know in the chat if you want to keep exploring, because this goes beyond that. We'll check one interstellar object before we wrap up tonight, but I want to at least get through the solar system. There's so much to explore in here, though. So much to talk about. Okay, next one. Let's go to many people's favorite, Saturn. Here's the ring planet Saturn, and look at that. It's simulating the shadows cast from the rings. Isn't that incredible? So you get to see it, very fine detail too. Look at the shadows of the rings themselves have those layers, those individual ring structures, just like you see up here in the actual structure of the rings. There's A ring, B ring, C ring, and so on. You can see those cast as shadows there as well. Now, the planet itself isn't too detailed compared to Jupiter, the other gaseous world. It has banding, for sure, and you can make that out in telescopes, but it's not as distinct. If you could see the top of the planet, there is a really interesting storm up top. It's a hexagonal storm. Nice bluish color. We have taken images of that storm. So instead of having a side hurricane red spot storm there, it has a hexagonal storm at the very top of the planet. Saturn is the second largest planet in the solar system. Oh, look at the shadow cast from the planet itself on the rings. So much detail when you have that actual light source coming from the sun that's being simulated. And one thing I really like, if we do this and line it up, you almost get that Hubble image where it's backlit from the sun. Oh, not Hubble. It wasn't Hubble. It was New Horizons or Voyager, one of the two, or both. We turn the exposure up a bit. That's effectively what that spacecraft took a picture of. And you can simulate that in here. You can also see the very outer ring of Saturn. Isn't that neat? I love that view. Can we find the pale blue dot? Is this it? Nope, that's Ceres. Yeah, I can't say exactly. Well, Saturn is invisible to us right now, so my guess is it's too close to the sun to see the Earth at the moment. So that might be our problem. Oh, yes, excuse me, Linda. Cassini. I don't know why I couldn't. Cassini was the satellite that orbited Saturn for many, many years and eventually crashed into its surface. It actually ran into the atmosphere of Saturn to burn up so it wouldn't contaminate the other moons in the solar system. Or in the Saturn system. Okay, let's just do one moon, just because we are running out of time for tonight. That's Mimas. I want to go further out to Titan. That's Rhea. Titan's way out there. Look at that. There's Titan. Titan, again, is the second largest moon in the solar system. Ah, it's orange. Isn't Titan a gaseous world too? Well, no, it's just like Venus. It has a pretty thick atmosphere. In fact, look at this. The atmospheric pressure is 1.47 atm as an average atmospheric pressure. If the Earth is 1, that's not too far off. Fascinating. Okay, but the temperature is negative 178 degrees Celsius. Oh, too cold, too cold. And its atmospheric composition is nitrogen and methane. Well, methane is a very potent greenhouse gas, so that's why it has a significant greenhouse effect. However, it's just too far away to warm up like like the Earth or like Venus. It can't collect enough solar energy to heat itself up. Move Titan from Saturn to the inner solar system, things would change drastically. It would be a much warmer world. And the fact it has a methane on it is fascinating. Methane here is a gas on the Earth. We use it for fuel. But on Titan, it's so cold, so frigid that it actually rains methane. There's methane lakes. There's methane. Let me get rid of that window. There we go. There's methane seas. Cassini. It was the Huygens probe. When the Huygens probe, which is part of the Cassini mission, landed on the surface of Titan, it touched down. It sort of squished a little bit into the surface as if it was almost like muddy. And that's because it's pretty damp because of that liquid methane on the surface. So really fascinating world here. Now, the question is, can it support life at these temperatures and this composition of atmosphere and so on? Hard to say. But the fact it has organic compounds meaning they contain carbon being what a significant portion of what we're made of is carbon. We're carbon-based life forms, organic life forms. Might be possible, might be worth exploring. And they're looking into sending a helicopter to Titan. In fact, that in part, trying to fly objects like with powered flight on other worlds like Mars with the Ingenuity spacecraft that's there right now, sort of helps us prep for missions like these with Titan. If Titan's atmosphere is perfectly suitable for powered flight, if you can make a mission that's revolves around that, you can fly around the atmosphere of Titan, take a bunch of pictures all over the world, all over the moon. So fascinating. And again, it's just a really thick cloud layer, but when you look at the surface, I don't know if it will. Let's see what it does when we land on it. Land. Yep. What it shows us, because maybe it'll simulate. It looks like the sun. That's kind of weird. Let's try and jump up here. Flight mode. Now, the actual picture of Titan does kind of look like it glows a little bit just because they've had to use infrared cameras, much like Venus, to actually peer through the clouds and see surface detail. So that might be why it's simulating like this. But it's a fascinating world, and it's hard to wrap your mind around the fact that there are other places in the solar system that have atmospheres. Our nearest neighbor, the moon, is one of the most common experiences with another world. It doesn't have one, but when you're around Titan, there's actually a distinguishable atmosphere around it. Like if we jump back out here and go to Titan, if we jump back out to the outside of Titan and we line it up with the sun, we'll get that thin layer of atmosphere, just like we would around the Earth. It sort of glows a nice orange because of the methane. So that's what you would see if you flew around to the backside of Titan and lined up with the sun. You'd get this nice ring. You don't get that with the moon when we get an eclipse, for instance, because there's no atmosphere there. There's nothing for the sunlight to glow or cause to glow. Okay, so there is Titan, and you know what? We should see if we could spot Saturn here near Titan. Where are we here? Saturn. See what Saturn looks like if you were in orbit around Titan. That's always cool to see. Whoops, I can't type. Saturn. Where are you? There it is. Look at that. Saturn from Titan. But it'd be a brilliant view. Now, the thing about it is you'd really only get to see the rings as shadows because the moons of Saturn also lined up in a plane, just like the planets of the solar system and so on. So there is Titan and some of the moons of Saturn. Okay, let's wrap up here with the last few items. We'll go to, I'm going to pronounce this, I think, Zoe Lerner-Pontario, who has been from SPIF at Cornell. She, I think, was the one that informed us. And if you were there for that presentation, you'll know the Greek pronunciation of this planet is Uranus. So I'm going to pronounce it Uranus. You pronounce it, in your own way, but I'm going to pronounce it Uranus. All right, so here is another ringed planet, a little bit thicker ring than Jupiter. So it's actually visible. It was visible to the spacecraft that flew by it, like the Voyager probes. And it's not super thick, though. I mean, if we bump up the exposure, it gets a little bit better. But look how thin it is compared to what we were seeing with Saturn there when it's shining through the sunlight. Really, really thin ring system. Okay, bring it back down. Uranus has a lot of moons as well. The only planets without moons are Mercury and Venus. All of the other planets have moons. And, whoops, you can see them all right there. Quite a few. I think one of the largest ones is Triton. There's Titania. Oh no, Triton might be, no, Triton's around Neptune. There's Ariel, Umbriel, Miranda. It's a fun name for a moon, isn't it? Miranda. And there's a bunch of smaller ones as well. So this is another gas giant, but much smaller scale than Jupiter and Saturn. It's a nice tealish, dull blue color. Kind of would be a nice pale blue in a telescope if you were able to get it in one. Moving on to Neptune, the 8th and last main planet in the solar system. Last of the large planets, here it is. I believe Neptune also has a nice storm. There's one storm system on it. I thought there was one that was bigger than that, though. That might be it. Again, we might be flipped again. Let's let it rotate here. Rotates every 16 hours. Not too bad. Orbital period of 165 years. So Neptune. Oh, there it was. Sorry. Let me go back in time. I guess we'll just let it go and let it come back around. Neptune will not complete one orbit in a human lifetime. It is too far out. And I think the same case for Uranus. Maybe you'd be lucky with Uranus. I'm not, hard to say. I think Uranus is probably maybe 120. I didn't catch it before, but atmospheric composition. So it's made out of hydrogen, helium, and methane. Common trend for these gas worlds. Gas giants. There was the hurricane again, the big system. So even this far out, at negative 200 degrees Celsius average temperature, you are still getting intense storms on these planets. Fascinating. The amount of energy that still exists within these worlds. Like there's high winds. It's really impressive. And again, there's tidal forces that can produce really nice subsurface oceans on the moon still. These moons are actually doing some really cool orbital motions as they rotate around. So there's the system of Neptune. I think it also has a very thin ring as well, but much thinner than Uranus. Okay, let's have it stop here. Okay. And do we want to go to Pluto? I think we should maybe go to Pluto. So Pluto, again, is not a main planet anymore, considered a main planet in the field of astronomy. However, its story is interesting, and it's just as impressive of a world as any other in our solar system. So just because we consider it a dwarf planet now, doesn't necessarily downgrade it in any way. I mean, NASA still found Pluto important enough to send a 9-year mission there. It started in 2006, got to Pluto in July of 2015, called the New Horizons probe. And it was a fascinating reveal of this planet. In fact, why don't I briefly switch over to... I'll switch over to my web browser, and I will show you what Pluto looked like before, in the before times. Before New Horizons got there. Whoops, that's not what I wanted to do. Open image, a new tab. There we go. There we go. All right, let's switch over to the web browser briefly. So there's what Pluto looked like before. Not very impressive, and this was from the Hubble Space Telescope. You know, you're basically only getting a color gradient across its surface, or a dark and light gradient. Not much more than that. But it's the different sides, so it did get, you know, they did let it rotate through. All right, now I think it should be fully simulated in Space Engine, so we'll switch back there. And we're going to fly, do a nice gradual flight to Pluto here. Rotational period of 6.387 days. So not super fast, but you know, you don't have to wait forever. It's not like it's the same. Its orbital period is 248 years. It's good. It's not. They don't sync up in that way. All right. Compared to that image we just saw, this is what we get from Pluto from the New Horizons probe. At least some of the data from it. And if I bring down the exposure level so we can get a better view of the surface, oh, look at that. Pluto has a big old heart. That's the first feature. Probably the best side of Pluto was facing us that day. Now, I think they did get some dark data here. Actually, I don't see very much of it at all. Let's boost up the exposure here. Yeah, I thought they were able to get some dark data. I guess that's it up here. But this side, we just don't know what it looks like because this was only a flyby mission. They did not put New Horizons in orbit. That would have been way longer. They thought it was worth it just to get a flyby, and rather than take forever to get there. So really nice surface features we have on Pluto. And again, there's this big heart feature. Now you sort of got to use your imagination, but there's the first section of the heart, the first half, and then the other half is a little bit more apparent. And it looks like it's a pretty dynamic world too, not too different from Europa, right? You see these cracks in the surface? And more than that, it has an atmosphere, believe it or not. Very incredibly thin atmosphere though. It says it's 1 × 10⁻⁵ atmospheres, Earth atmospheres. So incredibly thin, but it's made of nitrogen. So the more you learn about Pluto, the more amazing the solar system becomes. Because just because you're far out in the outer solar system in the Kuiper Belt where Pluto is, doesn't mean that you won't be just as interesting as one of the inner planets like Mars. I hope to see another Pluto mission in my lifetime because when they first revealed these images, just like when they first revealed, you know, the first images from Perseverance or that video that we looked at a couple weeks ago, just the more we can unveil about these areas of the solar system that have never been explored before or seen by human eyes, the better off I think we'll all be. Just because that's what it promotes science, it promotes exploration, and hopefully we will see more of Pluto in the future. Now, again, with Pluto, orbital period of 248 years. Again, it's more than 2 human lifetimes for it to take one trip around the sun. So really far out there. Now, some argue, if you look over here, some argue that Pluto should be considered a binary planet. Do you see how big one of its moons are? Here's Pluto, and orbiting around Pluto is the dwarf planet Charon, or Charon. I've heard it pronounced both ways. But if we go to Charon, it's a spheroid, and it's really not that much smaller. So this diameter is 1,212 kilometers. Pluto's diameter is about double, 2,374 kilometers. So it's about half the size, but Pluto does not dominate its orbit, or rather it's doing more than just a wobble as Charon orbits it. So it's actually doing its own circle in place here as Charon orbits around it, because Charon is massive enough. And it has a significant effect on Pluto's gravity. Now, the other neat thing about Pluto is that it has like 5 other moons. They're much smaller than Charon, but this system is incredible. Pluto has more moons than the Earth. Isn't that fascinating? So again, you can almost think about Pluto as a binary system, but in this case, it is in astronomy, it's currently classified as a dwarf planet. And Charon is one of its moons. All right, so that wraps up the solar system exploration. Now, I promised I would give you, we'll call it a tease, I guess, of what we can continue to do if we, run a planetarium program like this once a month. We're still working out our future schedule for upcoming Friday night program, so maybe we can return to this and keep exploring the solar system. There's a lot of options in this program. You can explore exoplanets. So there are cataloged exoplanets in this program. Now, we obviously haven't sent a spacecraft there, or we do not have telescopes powerful enough to actually identify what an exoplanet looks like. But we do know what type of planet it is. We know its mass. We know whether it's a gas giant or a rocky planet. This program actually simulates and procedurally generates what you can do, what those planets could look like. So it's not the true, not the actuality, not the true science. It's using mathematics to generate based on a series of parameters. Okay, this is a rocky world. It has, this type of atmosphere potentially. This, listed off. It's this close to its parent star, so it's warm or it's cold, and it puts together as much real data as it can, but the visual data is, of course, going to be all simulated. So that's one of the examples that we can do as we explore extrasolar space beyond the sun. We can look at exoplanets around the galaxy and throughout the galaxy. So really, really cool there. I will give you this tease, though. We can go to Sagittarius A. Does anyone know what Sagittarius A is? You'll see it's right at the core of our Milky Way. Let's take a nice gradual 20-second trip through the galaxy. Gradual, I put in quotes. You can't see me right now, but this is way fast. Aha, what is this? All right, well, let's check it out. We'll orbit around here. Wow, really bright jets coming out of it. Okay. Sort of a disk here, right? Well, it's like a protoplanetary disk. Is this like a star forming? No, if we want to find out what this is, I think we'll have to reduce some of the brightness. Oh, maybe keep going. Oh, there's something there. There's something there. Aha. A black hole. So Sagittarius A is the supermassive black hole at the center of our galaxy, the Milky Way. Most spiral galaxies, if not all, have supermassive black holes at their core. And if we can we look right down the disk? Oh, there we go. Now you can see the full black hole. And what's really neat is it's actually simulating gravitational lensing. Do you see the stars around the black hole bending? Isn't that fascinating? So you're simulating the gravitational effects of a black hole as well, and you're getting those lenses there. Now, that's the other thing. When we look at it like this, we see it as a disk. Can't quite see it from above if we maybe reduce this here. Way low. There it is. There's the black hole. Bump this back up here so we see the jets. But when you're looking at it from the side, this is a flat planar disk. But when you look at it from the side, it bends the opposite side up so you can see it. And that's how black holes work. And this was proved by the recent image that came out, I think, a year and a half ago, 2 years ago. The first image of a black hole. Now, it's really more, this is the shadow of a black hole that we're seeing. We're not seeing the actual black hole itself, because the black hole, in principle, is the absence of light. It's sucking everything into it that's past its event horizon. And in that sense, it's just, we're seeing the absence and the shadow of the absence of light. But that's sort of semantic. This is the presence of a black hole that you end up seeing. And that image that came out is an example there that you can look up. The first one from M87, I think it was from. So we didn't get an image of Sagittarius A. We used a galaxy that was its core in sort of like these jets, right, were facing us. So there was no dust, no material to look through. That's the problem with ours, is we have a lot of stellar material to look through to get to ours. Might still be possible to get a picture someday, but right now it's a little bit challenging. Now, if we bump up the light again so we can see the stars around it, you can see there's a bunch of stars surrounding the core of the black hole. And we're actually able to see these stars and the effect the black hole has on them. And this is some real data right here. I think these have real names. S13, yeah. So if we go through time here, we're gonna have to really scale up the time speed. There we go. So we're at 10 to the 7th, 1 times 10 to the 7th power time scale. So much, much faster. But at this time scale, we're almost moving like a year every 5 seconds, it looks like. So a year every 5 seconds, this is how the stars move. And they're moving really fast. And we have measured their speed, the speed at which they're moving around the black hole. So this is one of the areas of space where you get dramatic movement in stars. Usually stars take a long time to see noticeable change. But here they're moving reasonably fast because of that huge source of gravity. They're moving more like planets than they are like stars. So you have all these stars at the core of our galaxy rapidly moving around the central black hole. Notice the black hole isn't sucking them in, though. Black holes are not, as one of my professors, my astronomy professors said, they're not cosmic space vacuums. If you get past the event horizon, then you have something to worry about. But you can reasonably and successfully orbit a black hole if you're in a spaceship and you do it right and you don't, fly right towards the event horizon. You can or now the other side of that though is that you will be time traveling if you're in vicinity of a black hole, just because of the sheer force of gravity, which is another topic for another day. But so the world might not look the same when you return home, but as far as the danger of a black hole, if there was a black hole between here and Alpha Centauri, it might not be much to worry about. Because we've survived this long with it in our presence, assuming it was there to begin with, which it's not. But they're not anything to worry about unless you get near the event horizon. So no worries there. The central one in our galaxy is probably more helpful than harmful for galactic formation and the like. Look at, there's a smiley face. That's fun. Okay, anyways, I'm just having fun now. Let's go back to Earth and we'll end the show there. I wish you could see me, but again, I can't get my camera powered up in time for that. So we will return home for the night, and I will answer some questions to wrap up the show this evening. Let's see, Earth. We're going to fly back to Earth. Whoa, light speed, Jesus. Okay. Oh boy. Okay, what's going on? All right, well, this is catastrophic. Okay, set current time. All right, we're calm, we're collected, and we will answer questions now. Let's do a nice gradual orbit if I can get that running. Center object, go to object, aircraft, spacecraft. There was supposed to be a way that I could get it to do a nice gradual orbit. Nope. Okay, it doesn't want to. I can't recall quite how to do that, but we'll try it another day. I wanted to, just while we were talking, to do a nice orbital motion, but instead we'll do a nice rotational motion. How's that sound? There we go. Okay, with the Milky Way in the background. How about that? Okay. Let's see what questions we have for the wrap up the show here. I'm going to scroll up a bit. And let's see. Kitty said like icy tectonic plates. I think I saw that earlier. I think that was in reference to Europa. And yeah, it kind of similar. You could potentially get some moving plates across the surface just because of how dynamic it is. If you get a big chunk of cracks making up rather a big chunk of the moon and ice, that might be something you'd get. I don't know if it exactly has analogous tectonic plates on its surface, but I don't see why not when it's moving on effectively a mantle. Just like we have a liquid rock underneath our crust, Europa has liquid water underneath its surface. So there's no reason those icy, especially since, ice floats on liquid water, it makes complete sense that you'd get that. Bernadette asked, do we know why Uranus and Neptune look blue? And, is it something? It must be something with their composition, right? Let's go back and look. Neptune. I guess it's methane and helium and hydrogen. Could be the combination, I guess. Like you think Titan has that orangey glow to it from the methane in the mix in its atmosphere. Here methane exists in the atmosphere, but it's mostly hydrogen and helium. But that's the same case for Jupiter and Saturn. Some scattering effect. I'm not sure why exactly they have their blue color because the compositions aren't too different. So if anyone knows has heard about that in the chat, please let us know and inform us. We're all here to educate each other. Good question. Brenda. Yeah. Kitty asked, can I turn on orbits? And yes, I can. That was actually the thumbnail for this video, was showing the orbits in our solar system. So if I zoom out here, whoa, there's the moon orbiting the Earth. We're orbiting the sun. Zoom out, zoom out, zoom out, and there is the structure of our solar system. And again, you're sort of seeing that plane, especially for, let's go like this, the inner and outer planets. So we're going to count 1, 2, 3, 4, 5, 6, 7, 8. Whoops. So all the main planets fall along this ring. The outer objects, like those we've tracked in the Kuiper belt, all come at weird angles. See that? So they're all jetting in at weird angles. Pluto does the same. It does not fall along the plane of our solar system. So that's, again, one piece of evidence for why Pluto is no longer considered one of the main planets. It also does not occupy its own orbit. It does intersect with Neptune's, or it gets closer to the sun than Neptune. So Neptune is the high-powered source of gravity in the orbit of Pluto. They don't occupy their own separate areas of space. Yeah, the black hole is really, really cool. I'm seeing a lot of interest in that when we flew there. Nicholas says, definitely downloading this program tonight. I recommend it. Again, it is a paid program, and you just make sure that you have the right requirements. I think the lowest, I just looked it up the other day. I think I have the picture saved. Let me look. So yeah, the minimum requirements, it needs a GTX 950 or a Radeon 8760 as a graphics card. Again, you might be able to run it on modern CPUs alone with their dedicated graphics chips, but that might be a bit risky because I don't see that suggested here. Recommended specs are to have a GTX 970 or a Radeon R9 290. If you want things to run really smoothly right off the bat, that might be the way to go. But anything better than that, it'll run awesome. I'm running this on for those that are curious, we're on this is running on a 3070, and it's really not doing anything. So if you have a higher, like 2070, 3070, you will have no problem. It's barely heating up. Brenda asks, that large hurricane spot on Jupiter, what liquid is it? So a lot of Jupiter, a lot of its cloud systems look a lot like flowing water or flowing liquid, but they really are just cloud systems, gaseous cloud systems of hydrogen and helium. So it's not effectively like raining on Jupiter in that sense. Not like in a traditional Earth-based hurricane, but the physics of the cloud system is very much like a hurricane, and I guess that's what I meant by that. Yeah, Dr. Gash, I was wondering about, like, if it was a scattering effect like Earth. The reason we have blue skies here on Earth is because of a scattering effect, where all of the red light is mitigated and we're left with blue light. And then when the sun gets lower in the sky, you sort of get a bit of a reverse where you're getting red light. I wonder if it is some kind of scattering effect, because I can't think of anything else because the composition is so similar between, Jupiter, Saturn, Uranus, and Neptune. Can I view Pluto up close with the orbits on? Kitty asks. Yeah, let me go back to Pluto here. Yeah, here's Pluto. There's Charon behind it. And yeah, you can see, that's actually this is really good, because you can see now the wobble of Pluto based on Charon orbiting around. So this wobble that you get if we travel faster through time, this wobble of Pluto is caused by Charon being a massive object in orbit around the main dwarf planet. So that's where we get that circular interior orbit, orbiting around the main orbital node. Yeah, I think there was one from Voyager. That was I think it was Saturn. I think Carl Sagan's pale blue dot commentary came from that Saturn image from Voyager. But Cassini certainly took a bunch of those as well. But that was when we were looking at Saturn and looking at that backlit view of Saturn with the sun. That's what we saw there. All right, well, I'll take a couple more questions if you have them, so put them in the chat. If you are new to the channel, please subscribe to us if you want to see more observing sessions, more planetarium programs like this. If you enjoyed tonight's content, please hit the like button. That shows your support for us and shows you what you're enjoying more than other videos, so we can better cater what you want to see from us in these virtual events. We will continue these Friday programs. We don't have next week scheduled, I don't think. I did not see it on our website. Let me check one more time. But we'll keep you updated on that. If in fact I do decide to do a observing live stream tomorrow night, I'll let you know as soon as the morning. I'm just going to let the skies go one extra step, leave it overnight to see if that seeing improves anymore. I might still run it either way, but we'll let you know on Facebook, and we'll put out a post on YouTube. So wherever you follow us, we'll update you with that latest info. Yeah, I don't see next week's. Sorry if you hear rattling and meowing in the background. He's a bit crazy right now. No, I don't see it. Okay. What did we have another comment here. Nicholas says, I do have a program suggestion. Oh yeah, feel free to share that. That's pretty neat, watching Pluto orbit. Do a little mini orbit in its system. If we zoom out here, we'll see. Yeah, you see how you see those arrows pointing to Pluto's orbit. This line right here is Pluto's orbital path, and it comes in at a diagonal to the main plane of the solar system. Let me refresh the page. I'm not sure if anyone submitted their final comments, if I missed any. Nope. Okay. Nicholas, if you want to share that with me I know you're on Facebook, so feel free to share that on. Oh no, here it is. A presentation on galaxies and nebulas and star clusters. It's certainly something. In fact, this would be a good program to to explore there. Both Stellarium and this one would be a good one to explore with those objects. So it's a possibility, and it's something I'd like to look into more. So yeah, we'll keep you updated there. Does Triton orbit backwards? Well, we can certainly test that out. Traveling to Neptune. Let's slow things down a bit here, though. Proteus, there's Triton. Yes, it does. Look at that. So Proteus orbits clockwise, at least from our, if we consider this a top-down perspective, or Proteus is orbiting clockwise, Triton is orbiting counterclockwise. Which is a pretty unique, fairly unique path for a moon to take around a planet. Cindy asked, do you know how much work went into the program to show all this? It is amazing. Yeah, I can't remember the developers behind this off the top of my head, but they did do amazing work on this on Space Engine, because it gives you access to Planetarium software at home, and I think it's still incredibly valuable to go to a planetarium, like, at a museum, or using Kopernik's inflatable planetarium, because that's a completely shared experience. You can point out things in the sky right then and there with the instructor and ask them, can you go there, or can you explore that? Our planetarium actually has a way to control with basic controls, like a game controller or on an iPad, so we can actually pass that off to you and make it an interactive experience. But this is something you can do at home, and I think it's more complementary than something to replace or substitute. So when you go to a planetarium, you go visit, you go check it out with an educator right then and there, and then you can go home and explore yourself. Our planetarium software doesn't work super well on a flat screen. So this was great for us to share this virtual experience with you. Okay, well, I have a crazy cat here who clearly wants to play, so I'm going to wrap up the stream for this evening, and we hope to see you again the next time. We'll post our upcoming programs on our website and on YouTube, so look out for those. And with that said, look up and dream big, and see you again soon.